At the end of this video, you should be able to identify how paleomagnetism provides support for the idea of seafloor spreading, and explain how seafloor spreading provides a mechanism for continental drift. Paleomagnetism. If you have ever used a compass to determine direction, you know that Earth acts like a giant magnet. Earth has north and south geomagnetic poles. The compass needle aligns with the field of the magnetic force that extends from one pole to the other. As magma solidifies to form rock, iron-rich minerals in the magma align with Earth's magnetic field in the same way that a compass needle does. When the rock hardens, the magnetic orientation of the minerals becomes permanent. This residual magnetism of rock is called paleomagnetism. Magnetic reversals. Geologic evidence suggests that Earth's magnetic field has not always pointed north, as it does now. Scientists have discovered rocks whose magnetic orientations point opposite of Earth's current magnetic field. Scientists have dated rocks of different magnetic polarities. All the rocks with magnetic fields that point north, or normal polarity, are classified in the same time periods. All rock with magnetic fields that point south, or reversed polarity, also fell into specific time periods. When scientists placed these periods of normal and reverse polarity in chronological order, they discovered a pattern of alternating normal and reversed polarity in the rocks. Scientists used this pattern to create the geomagnetic reversal timescale. Magnetic symmetry. As scientists were learning about the age of the seafloor, they also were finding puzzling magnetic patterns on the ocean floor. The scientists used geomagnetic reversal timescale to help them unravel the mystery of these magnetic patterns. Scientists noticed that the striped magnetic pattern on one side of a mid-Atlantic ridge is a mirror image of the striped pattern on the other side of the ridge. These patterns are shown on the screen here. When drawn on maps of the ocean floor, these patterns showed alternating bands of normal and reverse polarity that match the geomagnetic reversal timescale. Scientists suggested that as new seafloor forms at the mid-ocean ridge, the new seafloor records the reversals in Earth's magnetic field. By matching the magnetic patterns on each side of a mid-ocean ridge to the geomagnetic reversal timescale, scientists could assign ages to the seafloor rocks. The scientists found that the ages of the seafloor rocks were also symmetrical. The youngest rocks were at the center, and older rocks were further on either side of the ridge. The only place on the seafloor that new rock forms is at the rift in a mid-ocean ridge. Thus, the patterns indicate that new rock forms at the center of a ridge and then moves away from the center in opposite directions. Thus, the symmetry of magnetic patterns and the symmetry of ages of seafloor rocks supports Hess's idea of seafloor spreading. Wegener Redeemed. Another group of scientists discovered that the reversal patterns seen in rocks on the ocean floor also appeared in rocks on land. The reversals in the land rocks match the geomagnetic reversal timescale. Because the same pattern occurs in rocks of the same ages on both land and the seafloor, scientists became confident that the magnetic patterns show changes over time. Thus, the idea of seafloor spreading gained further favor in the scientific community. Scientists reason that seafloor spreading provides a way for the continents to move over Earth's surface. Continents are carried by the widening seafloor in much the same way that objects are moved by a conveyor belt. The molten rock from a rift cools, hardens, and then moves away in opposite directions on both sides of a ridge. Here at last, the mechanism that verified Wegener's hypothesis of continental drift.
Continental drift is a theory that proposes that continents can drift apart from one another and have done so in the past. 245 million years ago, today's continents were part of one giant landmass called Pangaea. A giant sea called Panthalassa surrounded Pangaea. Gradually, Pangaea broke into two pieces, Laurasia and Gondwana. By 180 million years ago, the North Atlantic Ocean and the Indian Ocean started to form. By 65 million years ago, Laurasia and Gondwana had broken into smaller pieces, and the South Atlantic Ocean began forming. Today, the continents continue to move at a rate of about 1 to 10 centimeters per year. The Pacific Ocean is getting smaller, while the other oceans are getting larger.
At this point, you should be able to identify how paleomagnetism provides support for the idea of seafloor spreading, and explain how seafloor spreading provides a mechanism for continental drift.